Chapter 4 discusses arithmetic functions and its implementations. First is half-adder. Half-adder is to add two numbers, but each number has only one single bit. So we have one number x, one single bit, another number y, a single bit. Then it produces two outputs. One is a sum of the two numbers, and then carry is there. So if we have both 0 and 0, sum is 0 and carry is 0. If x and y are 0, 1 or 1, 0, sum is 1, but carry is 0. When both x and y's are 1s, then we have a sum is 0 and carry is 1. So this is truth table for half-adder. We have two inputs and two outputs. For each output, we could apply K-map, two variable K-map, to find a simplified expression for that. And here is that. S is this expression, and the C is this expression. So out of these expressions, we can draw logic diagram for that. But you can observe that S is nothing but the exclusive OR of x and y, so this could be another logic diagram using the exclusive OR gate. Full adder is to consider carries from previous position. So we have 3 bits now, same as we are adding two numbers, each of which is one single bit, so x and y, but carry comes from previous position. In the position you have some result and it may produce a carry. So carry is taken care, which is coming from previous position. Then we have the same two outputs, sum and carry, for the next position. So here is a truth table for that. And out of the truth table, we can construct the K-map for S, K-map for C. And out of the K-map, we can derive a simplified expression for that. As to the carry, this is a simplified expression. As to the sum, we don't find any two adjacent cells, so we have an expression for this one. So out of those two expressions, we can draw the logic diagram. So here is a logic diagram for S. Here is a logic diagram for C. Full adder can be constructed using two half-adders, which is less simplified though, but we are going to use this structure for some other purpose in the later slides. So anyway, from the previous slide, we have derived that simplified equation for S is this, simplified for carry is this. But we manipulate the equation for carry a little bit differently. So here is the one. Between the two, this is a simplified expression and then this expression, they are functionally equivalent. So whether it's simplified or not is only the difference. If we use this expression, then we find that this part is x exclusive OR with y, and then those are already used expression for S. Expression for S, if we manipulate those expressions, then we will find that that expression is nothing but an exclusive OR of all those three inputs. So using those manipulated expressions, we can construct one full adder using two half-adders and then OR gate. So here we have one half-adder, and here we have another half-adder, and then S from this expression is exclusive OR of all three variables. And the C from this expression is x and y with z and x exclusive or y. So z and x exclusive or y. So this is how to construct one full adder using two half adders and one external gate, which is OR gate. We can construct this way. This is less simplified though, but we can use this structure to developing something else, a so-called carry look-ahead circuit. We are going to talk about that shortly. So using full ladder, we can implement a digital circuit that can produce an arithmetic sum of two binary numbers with more than one digit. For example, if we are going to add two numbers, each of those are with a 4, each of these, this is in a 4-bit. So we have one number in 4-bit and another number in 4-bit. Then to add those two numbers with 4 bits each, what you can do is we have 4 full ladders and cascaded this way. When you do arithmetic in adding those two numbers, we begin with the rightmost position, which is the least significant bit. We add those two, 1 and 1. Then sum is 0, and then we forward the carry to the next position. And so in next position, we add those two numbers with the carry forward from previous position. And then we put sum here, and then we produce a carry for the next position. So we should forward the carry to the next position. So using full ladder, the rightmost position, carry in is always 0, and then the rightmost bit is added, and the carry is forwarded to the next bit. And then from there, carry is forwarded to the next bit, and so on. In this way, we can achieve arithmetic sum of two numbers with more than one bit. But we have some problem in terms of calculation speed if we keep cascading these full ladders. Suppose we have a 16-bit number or 32-bit number, then we will have that many full ladders cascaded. And the computation is done when all the carries are propagated. So the leftmost bit position needs a carry from previous position, and that one needs a carry from previous full ladder, and that one needs a carry from previous full ladder, and so on. So leftmost full ladder must wait until all the other full ladders are done. So that is called the propagation delay. And if you have many bits, then sometimes the propagation delay is not negligible. So we should find some other means of accelerating this computing issue. So that is called carry look ahead, which means that for the full ladder in the left-hand side, instead of waiting the carries computed from previous position, don't wait it, but just calculate the expected carry in directly from inputs. That's the idea of carry look ahead. So carry look ahead is a circuit is developed out of the full ladder with two half adders. So this is a full ladder implementation using two half adders. So we have three inputs A, B, C, the two outputs S and C. We give a subscript to show the position of the full ladder. So the rightmost position, we have A0 and B0 and S0, and then the rightmost position produces a carry for next position, C1, and so on. So those are subscript represent the position of the bit in the binary number or the position of the full ladder. Using those labels, intermediate node, this part let's define as a PI, which is exclusive OR of A and B. The G is this point, which is end of A and B. Then sum is expressed as a P exclusive OR C. And the carry is defined as this AND gate is a P and C, and the OR gate is a G. So C is defined as this way. So here is a equation for S and C in terms of P and G. P and G are defined in these nodes. Then C0 is something coming directly for the rightmost position, least significant bit, so we'll assume 0 there. And then C1 is defined as, from this general expression, G0 or P0 and C0. Here, G0 is A0, B0. And the P0 is A0, B0. So overall, in C1, it's computed out of A's and B's. Here is A's and B's, A's and B's. A's and B's are direct input for this adding circuit. So there is no delay for C1. It's computed directly from inputs A's or B's. In terms of C2, from general expression, C2 is defined as a G1, P1, C1. And C1 is a carry from rightmost position, which means this position should wait until this position is done. So we try to eliminate that dependency. C1 is derived as follows in the previous step. So we substitute that one, then we get this equation, and then here is the equation or expression for C2. Now C2 is dependent upon G, which is A's and B's, P is A's and B's, G, P, P, and C0, which is direct input. So here the new expression for C2 is in terms of A's and B's, which are direct input. So C2 is computed directly from the inputs, not necessarily waiting for previous full ladder completed. Similarly, C3 is defined this way, and then we replace C2 by the equation developed in the previous step. Then this is an expression for C3. So C3 is here, which is a carry in for the most significant position. Generally, if we use this circuit, we have to wait until all the previous three full adders are done. But this equation says C3 is dependent upon A and B, A and B, A and B, A and B's, and the C0, which is direct input as well. So C3 is computed directly out of all previous inputs, and then C0. So for C3, you don't need to wait until all the previous full adders are done. So this is called the carry look-ahead circuit, which means carries are calculated in advance without waiting for the previous positions full adders are done. So with these derived equations, we can construct a circuit for carry look-ahead generator. So given P's and G's here, the carry 1, carry 2, carry 3 is implemented this way. This is only for carry look-ahead generator, so that full circuit for 4-bit adder will be something like this. So you have a 8-bit input, 4-bit for each number, and then we have a 4-bit as a sum output and one other bit for carry output. Now the box here is a carry look-ahead generator we designed in the previous slide. It looks a little bit complicated, but what you achieve is a speed up in operation, arithmetic operation. So we add lots of hardware, but we achieve is the speed up of adding operation.